In this video, we'll learn about Newman projections and the conformation of alkanes, specifically looking at methane, ethane, and propane. Now that we've learned a little bit about alkanes, let's think about how we draw them and the perspective we have of them and their stereochemistry. So when we talk about stereochemistry, that's a branch of chemistry that's concerned with the three-dimensional aspects of molecules. So what do these molecules look like in 3D? Because 3D is much more interesting than just looking at molecules in 2D. A couple things we know about 3D. Sigma bonds, or single bonds, are cylindrically symmetrical. That means rotation is possible around the carbon-carbon single bond in open chains. So what that means is I can rotate this bond right here, and these carbons will rotate with respect to each other. So we can take our front carbon and rotate the hydrogens and end up with our view like this. So that's the type of rotation we're looking at. We're really focusing on the rotation around this bond connecting two carbon atoms and how it affects our molecule. First, when we're looking at methane, because we want to start with all of them. Methane is a perfectly tetrahedral molecule. It has bonds of 109. It has bond angles of 109.5 degrees, and it's an sp3 hybridized carbon. So when we're drawing methane, drawing it three-dimensional, we want to draw it in 3 dimensions. So that means I'm going to draw my carbon atom, hydrogen pointing up, another hydrogen, and having just a straight line like that indicates those hydrogens and the carbon are in the plane of the paper. So they're exactly on that plane I'm drawing. What happens if I draw the wedge? That represents the hydrogen coming out towards you. So that'd be a hydrogen pointing towards you guys. And the dash is a hydrogen that's pointing away from you. If you have a model kit, I recommend making a model of methane here to really see that hydrogen coming towards you and the hydrogen going away from you. But this would be a good 3D representation of methane. 2 hydrogens are in the plane of the paper. One comes out at me. One goes behind, away from me. So it comes towards the viewer. And that one is going away from the viewer. And that's about all we can talk about for the 3-dimensional aspects of methane. Ethane, on the other hand, we can draw it a couple different ways. And a couple things. Ethane, that single bond that connects the 2 carbons that's highlighted here, that bond is not in a fixed position. That bond has free rotation. And because it has different rotation, I can form different arrangements. And those are called conformations. A specific conformation is called a conformer. Now, important thing to know, pure conformers cannot be isolated. So I'm not going to be able to isolate any of these conformers we're going to be looking at in any part of this video. And so there's a few ways we can describe ethane and look at ethane. We have what we do is the wedge and dash. This is probably what you're more familiar with. If I were to draw it 3-dimensional with wedge and dashes, it would look something like this. Or I can take this molecule and kind of rotate it a little bit. Instead of looking at it on the side, I'm kind of looking at it in the front. And this is what we call a sawhorse. And so all we've done is taken the molecule here and kind of turned it a little bit. And you can see the sawhorse. So we're looking kind of at the front of the molecule and then down that line so we can see all the bonds still. Or if we take this and turn it even a little bit further, we'll be looking, say it's our eyeball, looking directly at it this way, we can end up with what we call a Newman projection. And the Newman projection really highlights the location of the hydrogen atoms relative to each other. So we can see here in the Newman projection, this hydrogen, the red one, is pointing up. That would be this one right here. And on this side, this would be our dash hydrogen because we're looking at it from this side. And then this would be our wedge hydrogen. And then our blue ones, we can see the straight line here is pointing down, opposite of the one pointing up. Look, we have one pointing down now. So again, I highly recommend get your model kit out, make a model of ethane, and then you can look at it from all these different perspectives. And you can see how our drawings represent the same molecule, just kind of looking at it from a slightly different angle. And now Newman projections are the ones we're really going to be looking at here, the ones we're really going to focus on. And we like the Newman projections because it's a way of drawing a molecule where we look straight down the bond that connects two atoms. It allows us to see the different conformations of that molecule. And so if we look at a couple different conformations we can get, if we draw our Newman projection, we have a circle, line pointing up, two pointing to the side each, and another one pointing in the opposite direction. So here, looking at this Newman projection, the angle between these two hydrogens, that angle is about 60 degrees. And this is what we call a staggered conformation. And in the staggered conformation, we call it that because all the hydrogens are staggered to each other. Another type of conformation we can have for ethane is if we take that back carbon and I'll rotate all the hydrogens. So when I rotate all the hydrogens 60 degrees, now they're all directly behind the hydrogens that are in front. And we draw it just ever so slightly to the side so we can see it. But what's implied is that these hydrogens are directly in line with each other. In this conformation, the angle between the two hydrogens here, that angle is 0 because they're all lined up. We call this one an eclipsed conformation. And so what happens is our dihedral angle, that angle I was drawing, is also known as torsional angle. And so that's the angle that the two hydrogens appear to be separated from each other by. So that means the dihedral angle for staggered is 60 degrees. For eclipsed, it's 0. And this makes a difference. Having those hydrogens overlap with each other is not a favorable interaction because those hydrogen clouds start to interact with each other. They don't have enough space necessarily. So eclipsed is not as stable of a conformation as a staggered conformation is. Before we continue on, let's practice drawing Newman projections and how to go from the line bond drawings or skeletal drawings to a Newman projection. So let's say we have We'll call it bromoethane. And I want to draw it from the C1 to C2 bond. So C1 to C2. What we're going to do is we're going to take our eye and look at our compound from this direction. So we're going to look at directly head on from that bromine, which means when you draw it, our dot is that carbon in front. That's the bromine. That's the one with the bromine attached. And the big circle we draw, that's the second carbon. So carbon 1 is the dot, carbon 2 is our big circle. Then we got to attach our atoms to it. So when we attach our atoms, we can draw in either staggered or eclipse conformation. We'll practice staggered for now. So we draw 3 lines coming out of each one. That represents the 3 different atoms that are attached to that carbon. So since I didn't indicate a wedge or a dash here, I can just put the bromine on one of them. So I have bromine on the bottom, hydrogen, hydrogen. And then our back CH2 has just hydrogens on it. Let's try one more just to practice. We'll do it from a couple different ways. So here we have our compound. Here we have our 2-methylbutane. And we can draw it from a couple different perspectives. So first, we're going to go C1 to C2. We'll change colors. So C1 to C2, our eye is looking directly that way. Here, I'll make this a wedge. And then the hydrogen going back, that's a dash. So we have our C1 to C2. And we have some 3-dimensional aspects there, wedge and dash. Okay, so that dot, that's C1. That circle, that's C2. With me so far? So C2. And C1 have bonds coming out like that. C1, since it's the methyl group, is all hydrogen. C2, now we're going to have to figure it out. So first, we have a methyl group. And I have a CH2, CH3 group, ethyl group, and a hydrogen. So 3 different groups attached to it. If we're looking at it in this direction, the wedge here becomes this one, becomes this hydrogen. Or sorry, it becomes this bond. So that's where our CH3 is. Our hydrogen is on the other side, and on top is that CH2, CH3. And now I want you guys to try and draw it along the C2, C3 bond. Pause the video, try and draw your Newman projection. Let's see how you did. Okay, so along C2, C3, now our eye is over here, looking that way. So we're looking along this bond here, which means that dot is our front carbon, circles our back. Again, we're drawing in staggered because it's just easier to draw in staggered. So drawing in staggered, that front carbon, C2, has a methyl group on top, a methyl group on the side, and a hydrogen. So here's our methyl group on top, here's our methyl group on the side, and our hydrogen. And in the back, since I didn't give any indication of stereochemistry, that means this one's in the plane. It's in the same plane as this CH3. Which means that back CH3 is on the opposite side, same plane there, as a top CH3. And then I get hydrogens here. Not too bad. We can draw Newman projections. So now we can draw Newman projections. Let's start looking a little more at the conformational analysis. We'll start first with ethane. And if we plot out their energy differences because they're staggered versus eclipsed, and if we're rotating the hydrogens around, we can end up with an energy diagram like what's drawn here. So here, if we're looking at the two red hydrogens, we're slowly taking that front hydrogen and turning it 60 degrees each time. So if you take your model and you turn it 60 degrees, the hydrogen here will now be eclipsed with this hydrogen. That's what we have drawn here. And an eclipse conformation is not nearly as stable because of the torsional strain. And so what happens if we redraw our eclipsed one is there's an interaction between the two hydrogens, between these hydrogens, and these hydrogens. That interaction is about 4 kilojoules per mole. Not much, but there's a little bit. So each one of those is 4 kilojoules per mole. And so since each one is 4 kilojoules per mole, 4 plus 4 plus 4 gives us 12. So the energy difference, and because of the torsional strain between those hydrogens interacting versus staggered versus eclipsed, is 12 kilojoules per mole. So it costs 12 kilojoules per mole to go to this eclipsed conformation. And then if I take that front hydrogen and I rotate it 60 more degrees, now I'm back in a staggered. You go back to eclipsed, staggered, eclipsed, staggered. So you can see it keeps going back and forth. And we've rotated all the way around. So all of our staggered conformations we consider degenerate because they have the same energy. And that staggered conformation, the reason it possesses a more favorable interaction is because an occupied molecular orbital and an unoccupied molecular orbital are interacting with each other. And so that interaction causes the energy to become lower during a staggered conformation. So next one we're going to look at is propane. So if we draw a propane, it would look something like this. And so what we're going to do is we're going to take our eye, look down the bond. So we're going to look down the C1, C2 bond. So what that means is my carbon in front, that little dot, that's C1. Here's the hydrogens coming off of C1. That big circle in the back that we just drew, that's C2. Here's my bonds coming off of C2. I know I have to have 3 bonds. Now, C1, if you think about propane, draw a little bigger, has 3 hydrogens. C2 has 2 hydrogens and a methyl. So we're going to have to add all of these groups there. That front one, it gets 3 hydrogens on it. The back one, we have 2 hydrogens, and now I'll just draw CH3 for that methyl group. So this would be considered a staggered conformation for propane. And then again, I can take my atom and rotate that back carbon. I tend to like to rotate the back one. And we end up with our eclipse conformation. And in the eclipse conformation, now we have a CH3 and an H interacting. CH, and the other ones are just the H's. We know that H interaction is 4 kilojoules per mole. That CH3H interaction should probably be larger than 4 kilojoules per mole because CH3 is a larger group. So it's going to cause more torsional strain because it's larger. It's harder to move around that. Again, if you have your model kit and you make a model of propane and you try this, you can see it's a little bit harder. You can occasionally get that CH3 to kind of hit the hydrogen if you try. And so now if we want to figure out what that interaction costs, we draw our energy diagram again. So we have our dihedral angles versus potential energy. First, we started staggered and then eclipsed, staggered, eclipsed, staggered, eclipsed. That energy difference is actually 14 kilojoules per mole now. So that means 4 plus 4, that's 8. So 14 minus 8 gives us 6 kilojoules per mole. So that would be the energy required for that CH3 and that H to be eclipsed. It becomes 6 kilojoules per mole instead of just 4. You guys should be able to draw a Newman projection from a given compound and start to be able to draw an energy diagram of the dihedral angles.